Hello everyone, welcome to the UFS webinar. This webinar is hosted by National Weather Service, Office of Science and Technology. The goal of this webinar series is to enhance the communication and share advancements in all the aspects of the Unified Forecast System in both research and in an operational setting. My name is Bhavana Rakesh, and then I work with Young Shui, who is the program manager of WorstTI, to coordinate and deliver this webinar. Feel free to contact us if you have any comments and suggestions. Today's webinar is going to be presented by Dr. Fanglin Yang from National Weather Service Environmental Modeling Center. He will be introduced by Dr. Vijay Talapragada, who is the Chief of Modeling and Data Assimilation Branch, also from the Environmental Modeling Center. Before we get started, I wanted to quickly show you how to sign up for the webinar notifications and how to view archived information. So on the screen right now, you have the UFS portal, which is at ufscommunity.org. Upcoming events is highlighted in the upcoming events box. You can sign up for webinar announcements by clicking on this link. Subscription to webinar announcements under the Stay Connected section. And you can view previous recordings of the webinar by clicking on the webinar archive, also from the Stay Connected section. A couple of quick housekeeping things that I want to run by you before handing over the presentation. The microphone and webcam has been disabled for all the attendees except the panelists and the organizers. Please raise your hands if you like to be unmuted. We plan to make the presentation last for about 45 minutes, followed by a Q&A session the last 15 minutes. During the presentation, if you'd like to ask any questions, please type it in the question box, and then I will read it out to the presenter at the end after he's done going through his presentation. With that, I'd like to hand it over to Dr. Vijay Talapragada to introduce Fanglin Yang.
Thank you, Bhavna. It's a great pleasure for me to introduce today's speaker at the UFS webinar series, Dr. Fanglin Yang. He is currently the Chief of Model Physics Group at EMC under the Modeling and Data Assimilation branch. And he has a long career at EMC. For the past 16 years, he has been working on developing and advancing our global modeling systems. And he is the project lead for the GFS, starting with FE3 GFS that was implemented in 2019 and leading to the next upgrade that he will be talking about today. He also is serving as a member of various WMO committees, including the WGNI, the Working Group for Numerical Experimentation. And he's also a co-chair for the UFS RTO medium range and subseasonal to seasonal prediction application team. He has a PhD from University of Illinois at Urbana-Champaign, where his son also is now going. And he had a lot of publications in peer-reviewed public journals in the area of climate modeling, diagnostics, NWP. And he also has a lot of experience in maintaining and advancing our verification database that has served to demonstrate how good or how bad the GFS model is. So this is something that he has excelled in the past 16 years working at EMC. And today he will be talking about the next upgrade for the UFS medium range weather application, also known as GFSv16. So hand it off to you, Fanglin.
Thank you, Vijay, for the nice introduction. It has been a good pleasure working with EMC and also in recent years with Vijay to improve our GFS. Also, I thank the UFS this webinar committee, especially Yanxi, for inviting me to give this opportunity to present the GFS version 16 upgrade. So the title of my presentation is Development and Evaluation of NCEP's Global Forecast System version 16. First, I'd like to thank all the developers. You can see the long list. This project manager is VJ, and also the project lead by me and also Ross Streeton on the DA side. Also, probably 1/3 of EMC staff are involved in this effort. Also, this upgrade is made possible by with contributions from the community. I'd especially like to thank our external collaborators from CPC, GFDR, and the OARGSR, PSR, and also NCAR collaborators. Also, the NAAA and science operation officers also involved in the evaluation of the GFS version 16. This is my the content. First, I gave a brief review of GFS history, and then describe the science and the infrastructure changes of version 16. The third part is the evaluation, and at the end we'll talk about the benefits and concerns of version 16. And this is a rather busy slide. It shows the history of GFS in the past 40 years. So the model started in 1980 with a spectral model. It's a rhomboid truncation with 12 layers in the vertical. Up to today, we have 64 layers. So last implementation in June 2019, we still keep the 64 layer. In terms of truncation, we used the first rhomboid, and in 1987 changed it to triangular truncation. After that, we have been using the same spectral model up to 2019. We switched to the FV3, the phantom volume dynamic core. So we've also been using the sigma coordinate and changed to the hybrid coordinate in 2007. We are still in hybrid coordinate, but in terms of elevation scale, we changed first from Euderian, and then in 2015 using semi-Lagrangian. And as you know, in 2019 we changed to this phantom volume cubic sphere dynamic core. So in the past 40 years, not many changes, not only in the model structure, also in the data assimilation, model physics. I'm not going to describe that in detail. So over the years, this is the frequency distribution of 500 million correlation in the northern hemisphere for day 5 forecast. So each line represents the distribution, the daily alarming correlation over a year. So if you look from the left-hand side to the right-hand side, that means the alarming correlation is higher. You look in the PDF shifted from left to the right, means we have increased the forecast scale gradually year by year. If you look at right most in recent years, there has been not many changes after 2016. But overall, there's an upward trend of the alarming correlation. You can say numbers shows the annual mean alarming correlation from 1996 to last year. Another way to look at the performance is so-called useful forecast scales. That is, the alarming correlation is greater than 0.6. What shown here is the northern hemisphere 500 millibar alarming correlation for each year. So you can see from the 1990 around the 60s, the useful forecast up to nowadays 8.5 days. So the increase is about 1 day per decade for the useful forecast. This is GFS, but it's also consistent with other international models. Overall, GFS scale still falls behind ECMWF and the UK Met Office, but it's in parallel to the Canadian model and slightly better than the other international models. So in June 2019, we had the first finite volume efficiency-based model implemented into operation. We also updated the microphysics scheme from the simple one momentum and Zaka microphysics to GFT microphysics. The model configuration was CA768 for the deterministic high resolution forecast. It's about 13 kilometer. And the data assimilation, we made major changes to increase the ensemble forecast resolution from 35 kilometer to 25 kilometer, and still 8 members. The model type didn't change. The major change was the dicot FH3. We first time used the non-hydrostatic dynamic core, but the dicot was still run in operation in single precision to save computing time. And the physics is run in double precision. So we, as I mentioned earlier, we changed from the Zaka microphysics to the GFT microphysics scheme. And so we did a 3-year retrospective run to evaluate the version 15, showed overall the forecast scale improved in both northern hemisphere and southern hemisphere. So in northern hemisphere, the gain is about 0.01, and this you can see here, and the lower panel shows the difference. I'm not sure you can see my full screen. It seems there's bottom covered by. Okay. Another improvement we saw in 15 is the precipitation scale score. On the left-hand side is the equitable thread score and verified against gauge observations over the canals. And the x-axis shows the threshold, and the y-axis shows the forecast leading time. So from the top, this red panel, the difference between the version 15 and the older spectral model, you can say the equitable thread score was improved for all leading time and also the threshold. Another improvement we saw from version 15 compared to the older spectral model is the diurnal cycle. This was for a particular summer, 2018 summer, over the canals. The green line is the observation, the blue is the version 15, and the red line is for the spectral model. Definitely can say the version 15 matches better the observation for the diurnal variation. Another major improvement we found in the FV3 based GFS is the wind and pressure relation for strong storms. The black line is the base trunk relation. The red line is the old spectral model. You can see spectral model, even though the pressure, storm pressure can drop very low, but the wind speed is limited. And there's for the FV3 based dynamic core with slightly different variation for the vision scheme, you can see the wind pressure relation matches much better with the base trunk than the old spectral model. We still had some major issues from the version 15 implementation, and notably we have the excessive cold bias in the winter season. The synoptic scale system seems to move too fast. For strong hurricanes, the trunk forecast is less careful. We have some temperature cold bias in the stratosphere. And also the PBR immersion was not adequately captured by the GFS version 15. It was also probably in the old spectral model. So when we started to develop the version 16, we had a goal to improve most of the issues we listed here, if not all of them.
Fanglin, sorry to interrupt. We are getting a few comments that the entire presentation can't be seen, is there a way to hide the Windows bar at the bottom of the screen?
Yeah, that's a issue I've noticed too. Let me try it. Let me go to a different screen. Or maybe I cannot share that.
Yeah, you cannot share the screen, I think.
I have two screens. That's an issue here. I don't know how to handle this. If I use the
right click and then you get an option to choose to hide the taskbar.
full screen, right?
No, I don't see it.
No, I don't see that. Okay. Is this better? No. No, I'll try to explain if possible, since I.
So Fanglin, maybe you want to try to present it in the not the presentation mode, in the sidebar. Yeah.
Yeah.
To this way.
Yeah. It will be too small, right?
Small. Right. It looks small.
You can make it a little bit bigger.
You know what? I try to. Let me see.
Yeah, that's good.
You think this is better?
Yeah, this is better.
Okay. So when we started to develop the version 16, we looked at the history. If you look at the history of the GFS, we haven't increased the model vertical layers since 2002. So when that time we increased from 42 layers to 64 layers. So in the past 18 years, the model has been running with the same vertical configuration up to 55 kilometers. So we made the decision to increase the model top up to the mesopause and also double the vertical resolution. So this is the vertical structure of the version 16 in this green line. And we tried the different configuration, like the 97 layer. Also compared to this black line dotted the ECMWF 137 layer configuration. So the EC has a higher resolution in the upper atmosphere, but much closer resolution in the stratosphere compared to our version 16 configuration. Now the major changes to the model physics. As I said, we increase the model vertical layers and extend the model top to 80 kilometers. In terms of physics, we changed the PPR and turbulence scheme from this hybrid 80 diffusivity mass flux scheme to a scale wheel total kinetic energy based EDMF scheme. Also revised the background diffusivity as a stability dependent function. Introduced a new non-stationary quantum drag parameterization. Updated radiation code to calculate the solar radiation absorption of water clouds. Update the cloud overlap assumption. Update the microphysics scheme in terms of the computation of ice cloud effective radius. Updated the NOAA land surface model for the ground heat flux calculation over slow covered surface, and also introduced the vegetation impact on surface energy budget over the urban area. And this is also for the first time the wave model, the wave watch 3 model is coupled to the GFS, but it's one-way coupling. There's no feedback from wave to the atmosphere. A few highlights of the changes of physics on the model performance. First is the new TKE-EDMF PBR scheme. It's a higher order increase in turbulence representation, and it's less diffusive than the hybrid EDMF. It includes the moist process and the non-local momentum mixing. It has the strength cumulus top-driven turbulence mixing, and it's scale well, and also has interaction with the cumulus convection. This comparison with the TKE and hybrid and the TKE and EDMF against the notch eddy simulation. The top panel here is the cloud water, the lower is the wind speed. So this red line each panel is from the hybrid EDMF simulation, and this blue line is with the TKE-based EDMF. The black line is the RES, can they match much better with the RES with this TKE-EDMF scheme. For the impact of gradient drag, the non-stationary gradient drag on the forecast, this is the 2-year AMIP type style forecast at 192 resolution, say 192 is about 35 kilometer resolution. So left hand side is the current operation model version 15. Without this new gradient drag scheme, you can see the model is not able to catch the quasi-biennial oscillation. And this right-hand side, you can see it has the cubule-like feature in the stratosphere. The fourth thing is the prescribed based on the mirror 2 AGSM. It's very crude approximation of the source function. Overall, the cubule strength and also periodicity are still not right. We're still trying to improve this in the next version. But it's much better compared to the older version or the current operation model. Another feature we noticed in the version 16 is the temperature improvement in the stratosphere. Showing on the left-hand side, the top panel is the current operation model temperature at 1 millibar in the northern polar region for winter and 2019-2020. The black line is the analysis, the different color lines is the different forecast time. You can see the model gets colder and colder. With version 16, the model is performing much better. All the forecast different leading time matches the analysis much better. On the right-hand side is the water vapor, and it's a monthly mean and the annual mean from September 2019 up to the red corner, the May this year. It's compared to this water vapor distribution matches the UARS halo observation much better. We didn't show here the version 15, but this is the first time we were able to capture the signal variation of water vapor in this model. So the increase of model vertical resolution and the extended model top do show benefits for the forecast in the upper atmosphere. Another change is the cloud radiation interaction. For the ice cloud, we use the weather formula to compute the ice cloud predictor readings. This is a collaboration with GFDR. The work it reduces the cold bias in the troposphere. You can see the temperature difference in the lower left panel. It's a sensitivity test with this new scheme. Another work we collaborated with GFDR is to battle a model crunch issue. In our real-time parallel in early September, the model crashed a few times when there was a strong storm passing through Japan over a small island. So we worked with GFDR and found the model is unstable when there's steep orography. So we changed the two data filter and also put some limiter for the thickness for the Riemann solver with model very stable. This problem also occurred in the GFS model. So this benefit of both the GFS version 16 and the GFS version 12 implementation. In terms of when we copied into the wave, we actually increased the resolution over the octopolar region and also over the global grid, but we removed the few this coastal region grid that about a 4 kilometer grid. Also, it's the first time used the RTOF's ocean surface current force and the wave model, and also we input the wave physics. In this presentation, I'm not going to show any forecast or product verification for the wave part because of the interest of time. For major changes in data assimilation, there are not changes in data assimilation. Actually, increase the model vertical resolution involves not changes for the Jeff Waiter gave a presentation in his UFS webinar, I think a couple months ago. So I can be brief here. So we increased and changed the local ensemble comma filter using the LETKF to replace the root mean square filter. And for the first time, we included the 4-dimensional incremental analysis update. We turned on SKEB in the ensemble forecast, use a new variational quality control algorithm. Also use the correlated observation area. There's not of changes or update or use of new centered observation. For example, this clear sky readings data from API Mari and also this GPS RO data. Another major changes or new additions assimilate high density flat level wind temperature and moisture observation in tropical storm environment. This is the first time we did this in the GFS, and it showed a lot of benefit. Also, we start to use the new version of the CRTM. Here's the example, the impact of IAU on the forecast scale. You can see there's on the left is the wind, the middle is the temperature, and the right hand is the relative humidity with or without the IAU. And the red line shows results from the runs with IAU. In general, the RMS been reduced with IAU included. This is a collaboration with the ORR and the physics and science lab. Another change is the new variational quality control. So it's applied to conventional observation. The overall impact is positive, and especially to reduce the wind RMSE over the northern, southern, and also tropics. In terms of high density observation for storms, we did a test for a few seasons from 2019 and 2020 hurricane season. On the different side is for all storms. This red line is from the HDOB experiment. The black line is the control version 16, and the blue line, the green is from the current operation model. The improvement is more prominent for strong storms. You can see on the right-hand side for storms stronger than 50 knots. The improvement is up to 7 days, and it's significant. We also made a major changes in the infrastructure because we increase the model vertical resolution, the file size doubled. So we made a decision to move from the NAMCL basic battery to LETKF with compression. And the compression ratio is about 5 times, namely is reduced from about 34 GB to 7 GB for the history, atmosphere history file. And this is significant saved to our resources. Also, we included the inline post-processing in the forecast model. That means to reduce the I/O and makes the forecast model more efficient. One reason is also to use the inline post also because we are using the lossy compression to write out the history file. We have to run this post inline to take advantage of the higher precision of the history file. In terms of the cost, the current operation model uses about 350 nodes at this peak time. For the version 16, some doubled, a little more than doubled. So we'll be using about 760 nodes at the peak time for the including both GDS and GFS cycles. We conducted retrospective and real-time parallels for evaluation. It's about 1.5 years retrospective runs. Real-time panels still running. We included the 2018 hurricane season, and also others started from June 2019 up to this year. Now, on the part of evaluation, so the GFS version 16 evaluation is done independently by the EMC model evaluation group with contributions from the model developers, the NOAA, STI science operation officers, and also with contributions from the community collaborators. And this is a link to the website. There's rich information in this website. Most of the slides included below are picked from this website. As I mentioned earlier, I'm not going to show any evaluation for the wave and component. So first, the common strengths from all the evaluation. So there's a notable improvement in synoptic scale performance in the medium range forecast. As we noted earlier, the GFS version 15 has the progressive feature. The storm moves too fast to the east, and this has been reduced. It catches better the solution was earlier and improved the frontal position and the precipitation forecast. In this slide, what showed here is the 500 millibar alarm correlation. The top left is the global, and middle is the northern hemisphere, and the lower panel and left is the southern hemisphere. On the right hand side is the average for the entire period. It's about 1.5 years, but with different forecast leading time. The left hand side is for day 5. The red corners is numbers shows for the version 16 and compared to version 15. So the forecast, the performance improved for both northern and southern hemisphere. And if you look at the right hand side, the difference, they are significant up to 6-7 days for both global and northern and southern hemisphere. So if we break down for different seasons, you can say the improvement also significant and also consistent for all the seasons, starting from the fall 2018 up to the current season. So the right hand side of this version 16, the 500 millibar alarm correlation, you can say they are all better than the version 15, the current operational model. And this is a special case showing the version 16 comes better the synoptic pattern. And on the top left is the version 15, and the top right is the version 16, and the lower right is the GFS analysis. You can see the version, this for the Olga case, it's October 26. This, I think it's 20, should be last year. So it's a 6-day forecast. The version 15, you can see this 12 moves too fast and did not have this cutoff low, and the version 16 captures this feature much better than the version 15. And this is also noticed consistently in many other cases. In terms of COPF, the precipitation, also this verified against the CCPA, precip over the Canals region. And on the lower left is the difference between version 16 and version 15. You can see the improvement of the equitable switch score is consistent up for most of the thresholds. This 24-hour forecast. And there are slides, if you go to that website, you will find the improvement also significant for different thresholds and different leading time. And this is the precipitation bias. Also, the bias being reduced. So the version 15 upper left panel, you can see the version 15 for light precipitation, it has high bias. For medium range and intense precipitation, there's low bias. So you look at the difference. The version 16 reduce the high bias for light precipitation, and also reduce the low bias for medium and the intense precipitation forecast. This example, the West Coast bomb cyclone case, last year, November 27th. The lower and right panel shows the stage 4 analysis. You can see the version 15 basically did not capture this strong, very heavy precipitation along the West Coast, Oregon, the Washington area, and the version 16 has much better forecast in this area. Another improvement we noticed is the improved low-level temperature forecast. Remember, the version 15 has not cold bias in winter. It was a major issue for us. Actually, we delayed the implementation for that to try to improve, reduce the cold bias, but it still remained an issue for us to improve in version 16. What's showed here is the 850 millibar temperature bias. You can see the version 15 with forecast leading time. This forecast leading time is from 0 to 8 days or so. You can see the cold bias increase with forecast leading time. For version 16, this cold bias has been largely reduced. And the lower panel shows the difference between the version 16 and version 15. And the version 16 still shows somewhat not cold bias at the initial time. This somewhat related to analysis. In the right-hand panel, you can see it's the RMIS of the temperature. Also, in general, RMIS has been reduced in the version 16. This slide shows the temperature bias at 2 meters. So left-hand side is the bias itself. You can see the version 15, the blank line, also has increase in cold bias with the forecast leading time. In version 15 and version 16, you can see the cold bias has been reduced. If you look at the lower left panel, and that shows the difference. The version 16 is definitely much warmer than version 15 for the winter time. The right-hand side panel is the RMIS. Another improvement is the better ability to resolve shallow cold air mass and some associated cold air damming events. This example for middle Atlantic severe storm case. It's the February 6. This is the 3-day forecast. On this lower right panel shows the ramp analysis. You can see there is a strong, very shallow cold air pool over the Virginia and also Maryland region. For version 15, basically didn't capture this cold air pool. Version 16, you can see upper right has much better forecast compared to the ramp analysis. So this the backup team noticed this is actually the first time the GFS showed this capability, and it has been a non-standing problem for the GFS to capture cold air mass. Another example here is the Midwest, the precipitation type. And last year, there's one strong snow fall event in the Midwest, central and Midwest region. And the GFS basically is too warm and all is rainfall instead of snowfall. The version 16 captured much better this event and has this slow event. Also thanks to Ray Wolf from WFO to provide this slide. Another special improvement is the TC intensity and increased lead time for genesis. So with stronger cyclone genesis, the version 16 has the overall better track size and the intensity. This slide provided by Dan Hopperin. So it's kind of like a Taylor diagram. Everything is perfect if it has a value at 1, the upper right corner. The further one from this point, the larger the arrow. Overall, the version 16 has a lot better probability, the probability density, the probability of detection, and also has a lower frequency bias. But the version 16 has a higher false alarm ratio. So version 16 is more cyclone genetic than the version 15. In terms of the hurricane track forecast, this for the Atlantic, the left-hand side is for strong storm, and Atlantic can say to input up to 5.5 days compared to the current option model, and right-hand side for Eastern Pacific also input. And this is the case for Hurricane Dorian. Remember the operational model actually showed the hurricane hit the Florida and to the west side of the Florida, the Panhandle. But the version 16 has much better position, and the scheme didn't actually have a direct hit over the Florida. And the right turn, the version 16 forecast had a better red forecast 36 hours earlier than the version 15. In terms of intensity, also version 16 has better intensity forecast over the North Atlantic. You can see the version 16 is the red line and the blue line is the version 15. Also, the version 16 has less of a weak bias than version 15. It's longer forecast lead time. This example for the Hurricane Michael case, the version 16, the operational model showed much weaker intensity compared to the base track. The version 16 showed consistently better intensity forecast. Now it comes to the concerns, common concerns for this version 16, it has the increased rate of trunk bias at longer forecast time. You can see here, compare in the Atlantic, same as the version 16, GFS version 16, and tends to tend too early to the right. This is evident both in the along track bias and also cross track bias. Mentioned earlier, the version 16 has larger false alarm and in the western North Atlantic region. And with this, look at this slide provided by Dan Harper. You can see the red squares shows the false alarm. You can see the version 15 has much less false alarm in the western North Atlantic region. Version 16 has much more false alarm, but the version 16 also has a better detection ratio. Another is the convective available potential energy issue. The version 15 already has low bias, and same as the version 16 worsened the problem. This shows here is the for this summer, starting from mid of July to early September, this light black line is observation that the heavy black line is version 15 operational model. The red line is from the version 16. So we're still looking at the cause to better understand what's the why this version 16 has lower CAPE forecast. This example showing here, you can see in the central Midwest region, the version 16 on the right-hand panel, the difference, the version 16 has a much lower CAPE. This is the surface CAPE. Also show the this sounding at the Fort Worth and the Norman, Oklahoma. Basically shows the model has a much stronger PPR mixing, warmer and drier, deeper PPR and stronger mixing in the version 16. Almost there. So another concern is the lack of concentration, lack of improvement in the radiation immersion. We know the version 15 already had problems in forecast PPR immersion. We were hoping to improve this, but in the version 16, we had one version earlier had good improvement in the PPR immersion, but the stratosphere got cold. We had to revert to that change, and still, so in version 16, we did not make much gain in terms of PPR immersion forecast. This still remains to be an issue to be addressed in the future. So a summary for the GFS version 16 objectives. So I think we achieved most of our goals to have better forecast model, increase the model top. We have a better forecast in the upper atmosphere, and also improve the data assimilation algorithm. Or to address most of the problems we found in version 15. But it's still like the pure immersion remains to be improved in the future. And in terms of schedule, so we started the development right after the version 15 went into operation in June 2019. The code allow the version 16 and the package has been delivered to NCEP central operation for implementation. And the NCEP director has approved this implementation, and the tentative schedule is planned for February 3rd. The GFS versions and 16 will go live for operation. So what's the future? On future, what everyone knows there, we're going to work on the next is the coupled model, atmosphere, ocean, ice, and wave, fully coupled. used it for both the medium range weather and the seasonal sub-seasonal forecast. I'll stop there and take questions. Thank you.
Okay. Thank you, Fanglin. We have one question from Joshua Fu. He asks, do you have a few more words on the convection scheme used in V16? What are possible causes for TC false alarm in V16?
Currently, we're using the simplified Alcala-Schubert scheme. I don't have an answer for you right now why there's more false alarm. We did made some changes, like the cloud-based mass flux, the critical cloud-based mass flux. We need to understand more what's the cause for the false alarm.
Bhavana, can I ask a question?
Yeah, go ahead, Yan.
Yeah, Fanglin, you have shown one of the concerns is the CAPE, the convection potential, what's that? Convection allowing potential energy by its low. Is that also low in the initialization?
This is mostly the model issue, and I don't think much does not have much to do with the analysis. It should consistently from the model from beginning to the end and to the extended forecast. We actually have been looking actively what's the cause and to understand better. One thing I mentioned earlier, because we had to increase the background diffusivity and to make the lower tops warmer and to make the mixing in the PPR stronger, that hurt the CAPE forecast. And also we applied a GR test called to initialize the land surface condition. So far we found it has probably made the land surface slightly drier. That also reduced the CAPE forecast.
Hi, this is Jeff Manikin, the model evaluation group lead, and I'm just going to expand on what Fanglin said. If you look at, say, a 0Z valid time, you do see a bias in CAPE at the start, but it's fully based on a diurnal cycle. If you were to look then from that 0Z forecast, if you looked at the forecast valid at 12Z, you wouldn't see the low bias, and then it would increase again in the late afternoon, go back to 0, then in the early morning, go back up the next afternoon. It's purely diurnal. So the initial conditions don't seem to be the issue, except perhaps, as Fanglin noted, the soil is very dry relative in V16 relative to V15. And that's something that's being investigated. We don't know if there's something in the physics that's drying out the soil, or if the physics are responding to the soil. Because if you looked at the soundings example that Fanglin showed, in all these areas where the CAPE is low, every afternoon, basically, we're over-mixing in V16. Yeah, that's it, Fanglin. And those, the red is V16, the OBS is the black, and V15 is the blue. And you can see there, if you look at those red lines in particular, they're notably drier than both V15 and OBS. You can see the PBL height is significantly larger. It's greatly overmixed, and that's drying out the PBL, which is leading to lower CAPE. But again, we're seeing drier soil in these areas. We don't know if the constant overmixing is leading to drying out of soil, or if there's something that's drying out the soil that is then leading to a response in terms of overmixing. But it's definitely, I think, a priority of EMC to understand this more, and their meetings, we're having regular tag ups here to try and figure out a path forward on this.
Thanks, Jeff.
The next question is by Cliff Mass. He asks, have you tried initializing GFS16 with European Center initialization grids to determine whether our main problem is the model or the initialization?
Differentially, when we started version 16, we did not have any ideal condition. All our physics development at the beginning used the ECMWF ideal condition. So I cannot conclude to say here pinpoint which physics problem is with the model. I think probably we understand here like the CAPE definitely issue with the model, not the data assimilation. But also we need to be also careful when we use the Fanglin analysis. So for our physics development, we saw some of the good results next for the NOAA MP when we run with the at the beginning using the ECMW condition showed very promising result. But later when in the cycle experiment, we found the NOAA MP was not behaving and has problem. So this is a question. So at what time, right time, or to what kind of physics update you need to run in cycle experiment, or what kind of physics upgrade you can get away with just focus on experiment using different ideal condition. Maybe I didn't answer your question, but I don't have a good one-to-one map, say the link, which physics problem is linked to the model and the analysis.
Next question is from Krishna Kumar. He asks, can you comment on GFSv15 versus GFSv16 forecast skill dropouts comparison?
Actually, we did not have many dropouts in the past couple of years. We did have one this year, actually very bad dropout. It showed up in both version 15 and version 16. So that didn't reduce the dropout or made it worse. But for that particular case, the version 16 actually is slightly better than version 15.
We don't have any more questions. Last call for questions, anyone? I guess that's it for now. Yan, would you like to conclude the webinar?
Thank you, Bhavana. Thank you, Fanglin, for the wonderful talk. Thank you for everybody, your interest. Please send us any comments, suggestions. We will try to improve this with time. That's all I have. Thank you.
All right.
Hope
Thank
to
you,
hear
everyone.
you next month.
Yeah.
Thank you,
Thank you, everyone. Have a good evening and be safe.